In chemistry, we use models to show us a simplified view of kind of how we think that things work. And so we work with the information that we have and we create models that are simplified views of reality, but that are useful in explaining a particular phenomenon. So there are limitations then to each of our models because they can't factor in every little thing, and there's exceptions to rules. And when you get down to teeny tiny levels like atomic particles or subatomic particles or even smaller than that, then things get pretty wacky pretty quickly. So when we talk about models for understanding the three-dimensional geometry of molecules, for example, like VSEPR, or when we're talking about bonding models, so the way that we understand how electrons are shared between two atoms through covalent bonds and things like valence bond theory, then we run into some stumbling blocks when we have different ways to represent the same element, but that give out or put out different behaviors that we would expect based on those models. So when problems arise, we have to reevaluate our models and we have to come up with a new understanding for how to explain different phenomena. So that's kind of what happened with carbon. And I want to talk about hybridization of atomic orbitals today, which is really more of an organic chemistry thing, because organic is the study of carbon-containing compounds. I am not an organic chemist, I'm an inorganic chemist, so hybridization is something that I don't interact with a lot in my personal research and field and studies, but it helps to explain some discrepancies that we see when we take something like looking at the atomic orbitals and then looking at the Lewis dot structure for carbon. So let's look at this. Let's look at where the problem comes from, and then let's talk about how scientists came up with a new model to solve this problem, because that's what science is, right? We identify things, we observe things, and then we ask questions about them. We come up with ideas, we test them, and then those best tested things become our new models and our new understanding of the way that things work. And then when we poke holes in those, then we come up with new models. So it's the scientific method in action. Okay, so what the heck is the deal with carbon? If we think about the energy diagram for the electrons on carbon, carbon is number 6 on the periodic table, so it has 6 electrons total. 4 of those are in the outermost shell here, and the outermost shell for carbon is the second shell, so our N is equal to 2. And when we think about our valence electrons, then if I was going to ask you, what is the electron configuration, you'd say, well, the valence electrons have an electron configuration of 2s2, 2p2, right? And we would show the energies like this. The p orbitals have a higher energy than the s orbitals, and this is what shakes out of that model of our understanding of quantum numbers, our understanding of electrons. We use the Aufbau principle, which is that counting up principle, to figure out kind of the order that the electrons are going to sit, and that's what it tells us. So if I look at that, and I think about covalent bonds, then I would say, well, a covalent bond wants to form when I have an electron that is unpaired, and that electron then wants to be shared with something else. So if I was to look at this model, I would say, well, I already have a pair of electrons here, but there's 2 of them in the p orbitals that are unpaired. So I would guess, based on this, that carbon wants to make 2 bonds because I have 2 places that it can share electrons. That's the definition of a covalent bond. And yet, when I do my Lewis dot structure for carbon, then I put my dots on there that represent electrons. I put them in my cardinal directions, and when I spread them out evenly, I end up with 1 on each side. And when I look at that Lewis dot structure, then I say, well, that carbon wants to make 4 bonds. And what we see is that that's the case, right? The Lewis dot structure predicts that carbon wants to make 4 bonds. Carbon does want to make 4 bonds. And of course, when I say wants to, I mean it's energetically favorable for carbon to want to make 4 bonds based on the way that it can share these electrons. So what that tells me as a scientist is that if this model jives with the behavior and the different measurements that I have, then there's a problem with this one, because this one tells me visually that I have 2 unpaired electrons, but that is obviously not the case. So there's something amiss in this model. So we have to come up with a new way of thinking about things. So that is where hybridization comes in. So maybe instead of it being distinct s and p orbitals, maybe it's actually some combination of orbitals. And then when I put them all together, right, because between them there's 4 and there's 4 here. And if I put them all together, then I could spread out all those electrons, and that would give me the 4 here. So maybe that there's some sort of hybrid that forms between the highest energy s and p orbitals on certain elements. And so we can think about those orbitals as hybrids. So let's think about this visually. Again, pardon my bad art. That is a running theme in my videos. Remember that s orbitals are spherical. So if I have an s orbital and 3 p orbitals, and my notation here means 3 as in the number 3, not 3 as in the principal quantum number. So I'm not talking about 3p orbitals, 3p orbitals. I'm just talking about 3p orbitals in general. If we have an s orbital and 3p orbitals from the same shell, and we think about them then as sort of being smashed together in a way, then that's going to give me 4 of these hybrids. So what do we call these hybrids? This hybrid is kind of, it's got a small little head. I think it looks like a little stink bug body because I'm not a biologist. So I have kind of 2 lobes still, so it sort of looks like a p orbital. My nucleus is in the small lobe. So if you're thinking about kind of the center of the atom and these lobes that come off of it then, so if I have these hybrid orbitals that are coming off around my nucleus in various ways in 3 dimensions, then that means that this larger lobe is available to do overlap. And the overlap is important because the valence bond theory tells us that overlapping orbitals give us covalent bonds. So a covalent bond can only form if there are parts of atomic orbitals that overlap in the axis of the bond. So this is going to create my bond axis. I'm going to have a nice big lobe that I can overlap with a number of other orbital types and create covalent bonds with. Okay, so this is my hybrid. Now what do I call it? Well, I have an S and I have 3 P's that went in there. So we'd have 4 sp3 hybrids. So the superscript there tells me how many p orbitals are combined with that s to give me these hybrids. Okay, so if we're thinking about this then in terms of our atomic orbital diagrams or our energy diagrams, before we said, well, it can't be this, right? It can't be that I have 2 unpaired electrons. Instead, maybe I can think about the energy of these things. If I have a hybrid, if they all look similar, then they're all going to have the same energy. They're all going to look energetically the same. So not this distinction between S's and P's, but now I have 4 of these hybrids and I can spread out those electrons evenly. And now that matches with my Lewis dot structure. That gives me 4 unpaired electrons. That matches the behavior of carbon when it combines together to form compounds. Now in terms of geometries then, this is going to be important. And hybrids are really most important in organic molecules because these carbon-containing ones are really the ones that are of the most interest because carbon is sort of special in this kind of context. There's many things that we can describe as having hybrid orbitals, and a lot of them fall in a carbon sort of region. They're definitely all nonmetals because we're talking covalent bonds. But when we're thinking about carbon-containing compounds, most of them are going to be organic molecules. Not all, but most. So I feel like to think about it in terms of the geometry, because that gets us back into thinking about VSEPR, and the geometry is going to tell us about the hybridization. And I usually think about it in those terms. If you know something about the hybrids, then you could predict the geometry, but I think it's easier to go the other way. We've already talked about how we can go from the Lewis dot structure to a 3-dimensional VSEPR structure, and from that geometry then, that can tell you the hybridization. So let's kind of talk about how. If I have linear geometry, recall that that means that I have a central atom with two things that are on opposite ends of each other, right? So the furthest apart that things can get in a structure is the opposite ends of a central atom. And so that three-dimensional structure is just a straight line, right? And the number of orbitals that would create that straight line are the number of electron pairs that that geometry would have. So linear geometry has two electron pairs. That means that there's going to be two hybrid orbitals that are creating that. And the hybrid then is going to be the total number of orbitals that I put together has to be 2. So it's going to be an S and a P. So we call that an SP hybrid. Now note that if I'm only hybridizing one of the p orbitals, there's a couple p orbitals left over that are unhybridized. So there's actually 2 p's that are, we call them unhybridized. But what we mean by that is that they're just p orbitals. Those p orbitals are hanging out on their own, and we'll talk about how that works in another video when we talk about double and triple bonds and hybridization. Now trigonal planar, if we're thinking about a geometry, that geometry occurs when there are 3 things around a central atom. So that would give us 3 orbitals around that kind of central atom. So the nucleus and that tiny lobe and the bigger lobe that is coming out in that Mercedes-Benz 120-degree angle sort of way. And if I'm doing a hybrid, the number of orbitals in is the number of hybrids out. So that would give me sp2 hybrids. So again, 2 p's and an s give me the 3. And there would be 3 of them. That leaves 1 p orbital that's unhybridized. So that 1 p orbital is hanging out, and again, we'll talk about the implications of that in 3 dimensions in another video. Tetrahedral geometry means that there's 4 things around a central atom. So that would be 4 orbitals total that would give us tetrahedral geometry. The number of orbitals in is the number of hybrids out. And when I put all those together, that's going to give me that sp3 that we talked about before. So all 3 of the p orbitals at a specific shell plus the s from that same shell. When we put them together, we end up with those sp3 hybrids. And that gives us tetrahedral geometry. Those 4 sp3 hybrids will orient themselves around a central atom. Now, trigonal bipyramidal is 5 things around a central atom. So we're going to need 5 hybrids in order to get us that. And now you can see I've run out of p orbitals. So we're going to start bringing in some d orbitals. And shifty d orbitals are really responsible for a lot of things that can break the octet rule. So once I start getting anything over 4 orbitals, that's going to give me something that's giving me geometries that get kind of funky. So this is actually an sp3d hybrid. So we're bringing in one of the d orbitals. And then octahedral comes from 6 things around a central atom. And so if we're following our pattern, because we're good little scientists at this point, then we can see that I'd have an S, 3 Ps, and now 2 Ds. So we call that sp3d2 hybridization that gives us octahedral geometry. So let's think about how this plays out then. If we think about something like methane, which is CH4, then when we draw it as a tetrahedron, well, let's just start from the beginning. Let's draw it as a Lewis dot structure first. So I draw it in 2 dimensions, and I say, well, there's 4 electron pairs, all 4 are atoms, so that means I have tetrahedral geometry, and the shape is a tetrahedron. So I'm going to draw it with those 109.5 degree angles, and there's my tetrahedral shape. If I'm picturing this from an orbital standpoint, then I have these guys kind of coming off, and then this one's coming out at you, and this one's going back in. And these are all my sp3 hybrids. And they can overlap then my s's from each of my hydrogens. So I'd have an overlap that's a covalent bond here that would give me those covalent bonds for methane. So this would be the way that we would understand bonding in a compound like this. If you have any questions, let me know. Otherwise, I will talk to you again soon.